everybody. In this video, we're going to go over an example that's similar to the one that you did in DL. Up to this point, we've primarily been thinking about energy conservation in terms of changes in various energy systems. If energy is conserved in a problem, then the changes in the individual energy systems all must add up to zero. However, there's another equivalent way of thinking about energy conservation, and that is to say that the total amount of energy in a system is constant. This means that if we calculate the value of the total energy at one moment in time, we've calculated the value for all moments in time so long as energy is still conserved. In this example, we've set up a system where energy is conserved. This individual is holding this ball 1 meter above the floor. They're going to drop the ball, and we're going to try to figure out how fast it's moving when it hits the ground. We could analyze this using an energy interaction diagram, but let's do it a slightly different way. There's another concept that we're going to be thinking about when we're doing this problem. One of the interesting things about gravitational potential energy is that its value depends on what you call the zero of height. If, for example, I'm interested in gravitational potential energy in this room, I might pick the floor to be 0 and then call this height 1 meter, such that if I were to drop this marker, its initial height would be 1 meter and its final height would be 0 meters. But this floor is on the second story of a building, so why not pick the first floor to be height 0? While we're at it, why not pick the roof to be height 0, or the center of the earth? It turns out it doesn't matter what we pick as long as we're consistent throughout the problem. In this example, we're going to pick y equals 0 to be 4 meters above the floor. This means that the initial and final heights of this ball are actually negative, meaning its gravitational potential energy is also negative. This turns out to be totally fine. It's the changes that really end up mattering, and we're going to see why that's the case. Let's fill out this chart with these values. We're going to assume that the mass of the ball is 1 kilogram. Let's start with this first row. We want to start with y, which is the height of the ball at this point. Its max height is 1 meter above the floor. Well, y equals 0 is 4 meters above the floor. This means that the ball starts 3 meters below y equals 0. This corresponds to an initial height of negative 3 meters. So what's the potential energy of this ball when it's at its maximum height? We know that the gravitational potential energy of an object is just its mass times the gravitational acceleration g times its height. The mass of this ball is 1 kilogram. We're going to take g to be 10 meters per second squared. And its initial height, we just found, it's negative 3 meters. So its initial gravitational potential energy before it's dropped is negative 30 joules. Let's pause for a minute and think about this. We've just said that the gravitational potential energy of this object is negative. What does it even mean for an object to have negative potential energy? It turns out there's nothing wrong with thinking about things this way. Gravitational potential energy is something we define. It might be fun to imagine that every object has a small little accountant sitting in there keeping track of the object's energies, but that's just not the case. We made it up ourselves. It's perfectly allowable, therefore, to call an object's gravitational potential energy negative, even if it doesn't necessarily make intuitive sense to us. What about the kinetic energy of the ball at this point? Well, we know that the ball is being dropped from rest, and so the initial kinetic energy is just 0. So what's the total energy for this object? Gravitational potential energy and kinetic energy are the only quantities we're considering. And so the total energy is just 1 plus the other, negative 30 plus 0, which just equals, of course, negative 30. Now remember, we're still thinking about energy conservation, except we're thinking about it in a slightly different way. Instead of saying that the changes in energy add up to zero, we're just saying that the total energy always has to be the same. We found the total energy for one point in time. Since energy is conserved in this system, we've now found our total energy for every point in time, for every height of the ball. So let's just write in the total energy everywhere since we know it. All right, now let's consider the other two heights that we're interested in. Those heights are halfway between the max height and the floor. We'll start with the halfway mark. If the maximum height of the ball is 1 meter above the floor, then halfway between the max height and the floor is just half a meter above the floor. So what is the value of y in this case? If you said -3.5 meters, you were right. The initial height of the ball is -3 meters, and the height that we're interested in now is half a meter below that. So the height is -3.5 meters. If we again just use the definition that gravitational potential energy is equal to mass times the gravitational acceleration times the height, then our potential energy at this point is just -35 joules. Now we're interested in the kinetic energy. There are only three energy terms in this problem: kinetic energy, gravitational potential energy, and total energy. We know that kinetic energy plus gravitational potential energy always has to equal the total energy. However, we already know the gravitational potential energy and the total energy for when the ball is halfway between its maximum height and the floor. And so we can just plug in what the kinetic energy must be. If the gravitational potential energy is -35 joules and the total energy is -30 joules, then the kinetic energy is just whatever it needs to be to make up that difference, in this case, 5 joules. Now let's do the exact same thing, except this time we'll do it for the point where the ball is just about to hit the floor. What is the height of the ball in this case? We know the maximum height of the ball was -3 meters, and we know that the floor is 1 meter below that. So the minimum height of the ball is -4 meters. This allows us to figure out the gravitational potential energy of the ball at this point. It's -40 joules. So if the gravitational potential energy is -40 joules and the total energy is -30 joules, what must the kinetic energy be? If you said 10 joules, you were right. -40 joules plus 10 joules equals -30 joules. The key thing to take away here is that knowing the total energy at every point allows us to solve this problem in much fewer steps than it would take with an energy interaction diagram. That may not always be the case. Some problems lend themselves better to energy interaction diagrams than others, but this is an example where working with total energy instead of changes in energy turned out to be more useful. Now let's see if we can graph this. I'm going to move over to the next whiteboard to give us some space. Let's try to put the data in this table on a graph. On the x-axis, we're going to put the height of the ball. And on the y-axis, we're going to put the amount of energy. We're going to put all the energy systems on this one graph. Let's start with the total energy. Because it's the simplest, it's always the same, -30 joules. Keep in mind, we only have data for between heights of -3 and -4 meters. So our graph should always stay between the -3 tick mark and the -4. What's the total energy for this period? Well, it's just the same all the time. It's -30 meters. So let's draw that in here. This line just says that when the ball is between -3 meters and -4 meters, its total energy is a constant -30 joules. Next, let's do the potential energy. To do this, we just need to draw in our points. We know what the y values are, and we know what the potential energy values are. So let's draw in those points. Here are our 3 points. When the ball is at a height of -3 meters, the total energy and the gravitational potential energy are the same, just -30 joules. When the ball is at a height of -3.5 meters, the gravitational potential energy is -35 joules. And when the ball is at a height of -4 meters, its gravitational potential energy is -40 joules. Lastly, let's draw in the kinetic energy of the ball. To do this, we'll just use the same process that we did with gravitational potential energy. What is the kinetic energy of the ball at height -3? It's just 0. We're dropping the ball from rest. What about when the ball is halfway between its maximum height and the floor? Well, that takes place at a height of -3.5 meters, and the kinetic energy at this point is 5 joules. Lastly, what about when the ball just reaches the floor? Well, we know that this occurs at a height of -4 meters, and that the kinetic energy is 10 joules. And here's our completed graph.
Look at this graph.
There's a lot of empty space, but this is an indicator of our choices. If we had picked, for example, that height 0 was at the floor, then our whole graph would be over here, near the origin. I did this on purpose to show why it's important that you pick height 0 carefully. If you're doing a problem like this, picking height to be 0 at a point that has nothing to do with your problem, in this case way above the floor, is probably not the best solution. It's generally a good idea to pick height to be 0 at a point that is actually of interest to the problem. For example, we could have picked height equals 0 to be the maximum height of the ball. If that were the case, the initial gravitational potential energy, and therefore the total energy, would have been 0. 0 is a nice, easy number to work with, so that would have been convenient. Alternatively, we could have also picked height 0 to be on the floor. If this were the case, then the final gravitational potential energy would have been 0. However, this is a perfectly valid description of this phenomenon. The location that we pick for height 0 does not change our prediction. Namely, our prediction is that when the ball reaches the floor, it will have 10 joules of kinetic energy. This prediction would have been the same no matter where we picked height 0. It's generally going to be up to you to decide which choice is best.